9.3 use basically similar conditions. The only difference is that it instead have an infinitely large plate, it has a finite plate. And that with a width of 50 millimeters. So what's the finite plate, of course, the complication which introduces in the calculation of Ki. So now Ki, instead of just sigma square root of IA, you have another term. Okay. So now you can see that the equation of K for the stress intensity factor is much more complicated because how they depend on A. So when you go do your integration over here, now that equation becomes much more complicated. So when you have that, obviously you probably will not be able to solve by hand. So let's see what so we'll follow similar step. So the first one is I want to find the critical crack and C. Okay, so what we can do in this case is, we do one thing here, because in my Excel file, I kind of simplify this equation a little bit. So that is equal to sigma square root of 2e, because the pi a cancels out times tangent. Okay, so what I show over here, so when you get into a little bit a complicated equation like that, you know that you cannot solve for by hand. What you can do is you get to the Excel, and then the first thing I can do to find the critical crack lengths, I can just get a bunch of crack lengths, and then I use that equation to calculate. So if you look at the formula there, it's just the equation I wrote down, and then calculate the Kmax I have. So now I can see that if my K1C is at a 60, I have it over here. At 70 millimeters, I just cross 60, right? So that means my my AC is going to be very close to 17. So I just take those two numbers. Or I can also plot this to see. Right. So now I plot it out, and I really shouldn't use a curve, or at least I should show the calculation point. Probably it's easy, just. Okay. So I can see that I'm crossing the 60 megapascal square meter K1C at that point. So this is my crack, my threshold. So from that, if I take those two numbers, I have my at A equal to 16 millimeter, my K max is equal to 56.14, and at A equal to 70 millimeter. So if I do an interpolation, I will get my AC is equal to 16 plus 60.72 minus. And that will be as we expected, that's very close to 17 millimeters. So the second one is a little bit more complicated. So we need to find the fatigue life. Okay, so in this case, because my A, if you remember, this one actually look like a linear, but you cannot really treat it as a linear. So if I make the axis a little tighter, it look less linear. So in this case, what you need to do is do the integration numerically. So basically you choose the correct growth from two small points. So AI plus 1 is just slightly larger than AI. So the idea is that within, if you take small baby step on AI, your delta K is almost constant, right? Then you can do the integration. So this is essentially kind of a numerical integration. So you have, this is your A and your NF, and we can look at how that looks like. And then what we do is we go from one step, from 1 to 2, we calculate that, and then we go from there, and then I add up until I get to my critical and critical. So that's what I'm going to do. So with that, of course, we go back to our equation. So we go back to our original equation over here, and then now we go just, or we can go back over here. Now we just do delta N and delta A. Okay. So what we take that equation, and so that delta N is equal to delta A over C times delta K. Now, because I'm taking the steps, I will put all subscript over there. And so delta AI will be AI plus 1 minus AI over C. So the question is that KIM. And that is equal to this equation over here, but it's changing with the correct length. So I'm just going to take the average of that. So I will have the Ki of AI plus Ki of. Or if you want to be more diligent, you can take multiple points in between AI and A plus, or you take very small steps between AI and AI plus. So this is again a convergence problem. Okay, so once you have that, of course, that now for that step is a constant. It's no longer a function of A, right? So in this case, it's a constant I call CI. So that constant change with every step you have. So then, of course, you can easily do the calculation. So that your NI plus 1 will be equal to NI plus. And then the critical length will be equal to that. And that's what you get. Okay. So go back to the Excel file. So for each crack length, I can calculate my delta K from my sigma max and the sigma mu, and then I can calculate my delta AI average. So basically, I take that and average it. So that is the crack. It is the stress intensity factor I will use to calculate K. So from that, I can calculate, okay, for the crack to grow from 5 millimeter to 6 millimeter with this delta K, and that's what the time will take. So it will take about 98, almost 100,000 cycles. And I do for each step. So the nice thing with Excel, of course, you can populate that done. So you only need to set the first few rows up and everything will populate that. So that's basically for every 1 millimeter of crack growth, how many cycles it will take you. So you can see that actually at the beginning, it takes longer time because the crack is shorter, right? As the crack grows, that gets shorter and shorter and shorter, which makes sense. So if your data show that it's getting slower and slower, then you will check to see if you did get it correct or not. And then for that, of course, you can also calculate your DAVM curve. Just calculation of how long it takes, and then you can add them up to be your number of cycles. So in this case, since 17 is very close to the critical crack length, so I can basically say it's slightly lower than that, right? If you want, you can put, so we had was 16, what was the critical crack length? 16.92, right? That. Okay, so yeah, that's very close. So it take about 500,000 cycles for that crack to propagate. Okay, so that's how you use the Paris law to predict when you crack or how much lifetime you have until the final the fracture happens. In this case, what we deal with is what we call the constant amplitude. So that means is that my amplitude does not change over time.